Hey everybody, Nick Gubbins from Colorado State University, back again, this time to talk to you about weathering, introducing the weathering module and discussing solubility. So let's leap right into it. So solubility and weathering are very important for water chemistry. We're very concerned with what is in water and if it will stay there or not. Weathering is just the process through which minerals are broken down. We're going to get into that more in subsequent lectures, but it's very important because it's the source of many of the solutes that we're interested in. So by the end of this video, students should be able to calculate the molar solubility of a substance and the solubility product constants, be able to understand the common ion effect on solubility, and understand the relationship between pH and solubility, and then get a basic familiarity with complex ion formation. All right, so solubility defined is just the amount of substance that can be dissolved into a solution until it reaches saturation. And that begs the question, what is saturation? Saturation is just when a solution is in equilibrium and it is in contact with a solid phase. So a simple example of that is, I'm sure a lot of people have made Kool-Aid or iced tea from a mix, and you can dissolve and dissolve and dissolve, mix into it until eventually there will be some that is left sitting at the bottom, and that the precise moment in which the little first grain of mix was on the bottom there, so just before that actually, is when we would say that the solution has reached saturation. Before that, we'd say it's undersaturated. All right, so how do we as chemists talk about solubility? Well, it's just the mass of some solute that can be dissolved in solution. So on the left here, we've got a picture of somebody dissolving table salt, so sodium chloride, into a glass of water. And so if we wanted to talk about the solubility of sodium chloride in water, we could talk about it in the amount of grams per salt that we could dissolve into the water. However, one thing that chemists are a lot of times interested in are the stoichiometry of it. So we'll like to talk about molar solubility, and that is just the number of moles of a given solute that can be dissolved in solution. And that is going to be in, unsurprisingly, it's going to be moles per some volume, usually liters. So what if we wanted to know what the molar solubility of table salt is? Well, we could do a really simple experiment. We could just dissolve, just like the person in that photo was doing. We could just dissolve table salt into a glass of water until it reaches saturation. So let's say the glass has a quarter of a liter of water in it, and we get 90 grams of salt into that, 0.25 liters. So time for some of the easiest math that this course will ever put in front of you. We've got 90 and 0.25 liters. How many can go in one? Well, that's super easy. We'll just do some cross multiplication. And then we can solve for x, and we get 360 grams of sodium chloride per liter. But we're interested in the molar solubility, not the solubility. And so we can go to our trusty periodic table and look up what the molar mass of sodium chloride is going to be. And it is right around 60 grams per mole. So we can go ahead and multiply that by the inverse so that we get moles on top, and we can cancel out the grams. And that gives us a molar solubility of 6.16 moles per liter. Simple enough. So how else do we talk about solubility? Well, we use a solubility product, or KSP, yet another K. And this K describes the equilibrium state at saturation. And just like all the other Ks that you've seen, it's just a unitless constant. But this one is specifically describing the extent to which a solid will dissolve into a solvent. And just like the other Ks that you've seen, it's going to be qualified with some range of, or some specific temperature and pH. pH we're going to get into later, but pH is very important for the solubility of some reactions and not for others. So for table salt, it is not a big deal, but in some it is a very big deal. So we've run our experiment. We've crunched out 6.16 moles per liter as the molar solubility of our table salt. What is the solubility product for table salt dissolution? Well, to start out, we can go ahead and write out the formula for that. So we have solid salt, and it is going to dissolve into a sodium ion and a chloride ion. And just like how we calculate all K values, we'll go ahead and do the product of the products over the product of the reactants concentration. In this case, because sodium chloride is a solid, we are going to omit it from our K calculation here. And so because we have 1 mole of sodium and 1 mole of chloride for each mole of NaCl that we put in, just plug those in. And the exponential ones here are just to show that if you had subscripts, this is where they would come into play. And then we can just do some simple multiplication, and we get a solubility product of about 38, which this is very, very high for a solubility product. Usually, chemists will use solubility products to describe the relative solubilities of pretty insoluble things, and table salt is very soluble. But to put simply, so the solubility product constant is the equilibrium constant for a saturated solution between an ionic solid and its saturated solution. It doesn't have units. Solubility is just the mass per volume, and then molar solubility is just the number of molecules of that solute that can be dissolved in a given volume. And we can convert in between them relatively interchangeably. So if we have a solubility, we can use its molar mass, its formula weight, and that can get us the molar solubility. So that was just dividing by the molar mass in my first example. And then if we have a chemical equation, so if we have an empirical formula for how it dissolves, then we can use that to get the molar concentration of the ions. And if we have that, then we can use our product formula, and we can calculate the product constant for that reaction. So let's do just that. So let's get the solubility from a KSP. So let's say you're a water manager, you're interested in adding fluoride to your water supply, and you want to see how calcium fluoride is going to work, how much you need to dissolve to get the fluoride that you want. So calcium fluoride dissolves in water through the following equation. And then we can set up an ice diagram. So initially, we have nothing dissolves. The change will be whatever is dissolved. And then the equilibrium will be what becomes dissolved. And then we can write out that empirical formula. So the product is going to be the product of those product concentrations there. And we know from looking it up in our chemistry textbook or some table somewhere that 3.9 times 10 to the negative 11th is our solubility product for calcium fluoride. So now we can go ahead and just plug in our equilibrium molar concentrations, which are going to be X and 2X. And then because there are 2 fluorides here for each one of calcium fluoride, we're also going to be squaring that term. So we can go ahead and square the 2x to 4 times x squared, and then multiply in the x. And that should get us 4x to the third. And then we can just divide our solubility product by 4, and then take the third root of it, and we get a molar solubility of 2.1 times 10 to the negative 4 moles per liter. So not all that soluble. It would take quite a bit of calcium fluoride to get a significant amount of fluoride into the water. Probably want to stick to something like sodium fluoride, which is what most water managers use. So the key concept here is the solubility product. KSP is a constant that describes the extent to which a solid will dissolve into a solvent. And the molar solubility is the number of moles of a given solute that can be dissolved per liter of solution. All right, we can get into the fun stuff now. So the common ion effect. There's a lot of words on this slide. Don't let it scare you. The common ion effect just says whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than if it were alone in solution. So in blue here is calcite, everybody's favorite mineral, and we can see that it has a KSP of 3.36 times 10 to the negative ninth. And then in red is gypsum, a similar mineral, and it has a KSP of 2.4 times 10 to the negative fifth. So from going from 10 to the negative ninth to 10 to the negative fifth, we can tell that gypsum is going to dissolve way more readily, so orders of magnitude more readily than calcite. And an electrolyte is just any compound that dissolves into ions in water. And so you can see calcite and gypsum here both dissolve into a calcium ion and then some other ion. So for calcite, it is bicarbonate ions, and then for gypsum, it's sulfate ions. So we would call gypsum here our strong electrolyte and calcite here our weak electrolyte. And so when we put them in together, we would expect that calcite is going to ionize less. So why is that? Well, if we look at both of these equations, we can see that they're both putting off, they're both, as products, they have calcium. And we know that gypsum is way more soluble than calcite is. And so if we remember to our Le Chatelier's principle, we know that if there's a bunch of calcium already in there, so if there's a bunch of calcium already in solution, which is a product of the calcite dissolution, that is actually going to shift the balance of the calcite reaction back to the left towards the reactants. And that means that calcite will be less soluble in water. So this happens in some natural systems. If you have a ton of gypsum that is dissolving in large amounts upstream, it will precipitate out calcite downstream, as calcium is that common ion. All right, another example here. This one's a little bit of a stretch, but let's say we have a mine and it spills out hydrofluoric acid into a nearby river until we have 0.2 moles per liter of hydrofluoric acid in the water. And then let's say we're near like a volcano and there's hydrochloric acid in the rain, and it comes down until the river has a concentration of 0.1 moles of hydrochloric acid. So if you remember from your acids and bases, hydrochloric acid, very strong acid, hydrofluoric acid, not that strong. So in this case, if we're thinking of this in the common ion lens, hydrofluoric acid is our weak electrolyte, it's going to ionize less strongly. Hydrochloric acid is our strong electrolyte, it's going to totally dissolve into water. And then the common ion here is the hydrogen ion, or actually the hydronium ion, but we like to, as chemists, abstract that out to the hydrogen ion. Okay, so we know that all the HCl will dissociate, or up to its solubility product. But how much hydrofluoric acid will? So because we're interested in the hydrofluoric acid, we can ignore the hydrochloric part of this, the chloride ions here. It's just a spectator ion. And we can focus in on just the fluoride. So the reaction for the dissolution here is hydrofluoric acid dissolves into a hydrogen ion and a fluoride ion. So initially, from our word problem, we know that there was already 0.2 moles per liter of the hydrofluoric acid. And then we know, if you imagine the hydrochloric acid has fully dissociated, we know that for each mole of hydrochloric acid, there will be a mole of hydrogen ions and of chloride ions. And just like that, there's also, for every tenth of a mole of hydrochloric acid in the river, there's also 0.1 hydrogen ions. So that's our initial. And then the change is just whatever comes out of, whatever dissolves from or dissociates from the hydrofluoric acid will yield us 1 mole additional of hydrogen and of fluoride. And so at equilibrium, we know that we have the existing concentration, so 0.2, whatever we started with, minus whatever dissolved or dissociated, and then in our hydrogen and our fluoride, it'll just be what was already in, so 0.1 from the hydrochloric acid added on, and then from the fluoride, nothing yet, so just X moles. All right, so rewriting that, we can look up the KSP of hydrofluoric acid, and we find that it's 6.8 times 10 to the negative fourth. So, especially compared to like calcite, gypsum, whatever, it's still pretty strong. But compared to hydrochloric acid, it's still very weak. And so we can write out our solubility product expression here, just like we've done in the previous examples. And then we can just go ahead and plug in our equilibrium values because this solubility product is at equilibrium. And then because we know that this is the weak electrolyte, we can go ahead and assume that whatever this change in X is going to be very, very small compared to the actual concentrations of the solution. And so we can, whenever we're comparing it to these existing concentrations, we can just assume that X is essentially going to be a rounding error, and we can discount it, which gets us out of a quadratic nightmare and instead gives us a pretty easy algebra question of solving for X here. And that gets us 1.4 times 10 to the negative 3 moles of fluoride in the water, which is much, much less than we would expect of a 0.2 molar solution of acid. Cool. So to sum up, adding a common ion decreases the solubility of compounds containing that ion. And the exact effect is going to vary based on that ion and the stoichiometry of the reaction. Now, I had prefaced this, or sort of brought it up before, that pH can be really important for some reactions. And that's very true. The solubility of many slightly soluble compounds is increased in acidic conditions. And that is because you have all this hydrogen ions floating around in solution, and those can react with the conjugate bases of these slightly soluble compounds, and that can move the dissolution reaction towards the products. So let's go back to everybody's favorite mineral, calcite. It's dissolving in water. What would happen if some hydrochloric acid got added to this? Well, we'd have a bunch of hydrogen ions in solution, and then those hydrogen ions can go ahead and react with our bicarbonate that comes from calcite dissolution, and it can form carbonic acid. So now that we have another reaction here, so this interaction is consuming bicarbonate and creating carbonic acid, that is going to move our calcite dissolution from the reactants to the products. And it's going to do that to keep equilibrium. And so this actually plays in a bit to the speciation diagram that you've seen in Anna's carbonate lectures. And at low enough pHs, eventually you will have this be the dominant, you'll have carbonic acid be the dominant species. But also you'll find that at these low pHs, calcite is very, very, very soluble. All right, so a real world example of this is ocean acidification. So the solubility product of calcium carbonate is 4.5 times 10 to the negative 9th. And this is, again, if you haven't memorized it yet, the solution, or the equation for calcite dissolution. And calcite is what table coral, like up in the top right, makes its bones out of. So the structure, its skeleton, essentially. So what's going to happen as we add pH? Well, spoiler alert from the slide before, that as we lower the pH, we're going to have more free hydrogen ions in solution. Those are going to react with the carbonate. It's going to create carbonic acid. We're going to have more calcium carbonate getting dissolved to maintain equilibrium, and this is not so good for you if you are if your skeleton is both in contact with that solution, so like in the ocean, and then and you rely on having calcium carbonate as your skeleton. So this is a huge danger for oceans moving forward, is as we dissolve more and more CO2 into the waters, they become more acidic, and as they become more acidic, calcium carbonate becomes more soluble, and as it becomes more soluble, it becomes harder and harder for these organisms to build their skeletal structure. So the key concept here is lowering the pH of a solution can increase the solubility of many slightly soluble compounds. All right, before we leap into ion complexation, the last learning objective, let's do a quick review of Lewis acids and bases. So a Lewis acid is something that accepts an electron, or accepts electrons. A Lewis base donates them, and then when one donates and one accepts, they form a covalent bond. So here we have a water molecule and we have a hydrogen ion. In this case, the Lewis acid, unsurprisingly, is the hydrogen ion. It is accepting electrons, it's positively charged, and then the Lewis base here is the water, and then together they are forming a covalent bond to create the hydronium ion. So how does this work in ion complexation? Well, metals can act as a Lewis acid toward water, so they can accept electrons from water because they're generally positively charged. Then water, in this case then, just on the inverse of that, is acting as a Lewis base towards metals. But it's not all that strong because water is polar, and as you saw on the other slide, it's not actually charged or anything. It's just polar and has some relatively free electrons to move around. And so if another stronger Lewis base is in the solution, it can essentially pop off one of those waters and replace it with this complex. So here is aluminum hydroxide, so AlOH4 negative, and this is a complex ion. And so any metal and all of its Lewis bases together form this complex ion. So what effect does this complexation have on solubility? Well, generally it makes the solubility of the metal higher. And that operates on the same principle as the pH or the common ion effect, but basically it's just Le Chatelier's. So if you have your metal is tied up in all of these different complexes, it allows for more of that original compound to dissolve. So let's do an example of this. So here is aluminum hydroxide in the presence of a base, and it dissolves. So under basic conditions, as AlOH4 forms, more is going to dissolve to create to keep the equilibrium. So how does that work? Well, the actual form of Al3+ is Al3+, and then it has a bunch of water molecules essentially magneted onto it that are providing charge stability around it. And so in the presence of a base, which is a much stronger Lewis base, unsurprisingly, so a hydroxide, kind of the classic base, if that is in solution, it's a much stronger Lewis base than water, and it can displace that. And so you can form AlOH2+. And if there's still more base in solution, then it can form AlOH2 with a plus. And with even more, it can displace another water and can be at AlOH3. And then if it's in very basic conditions, can be AlOH4-. So the net of it is that this aluminum hydroxide, under basic conditions, can form into AlOH4-, but that there are actually several ion complexes along the way that it is forming and that it can also exist in. And so to look at that another way, let's look at a speciation diagram. And so this is the same sort of diagram that you've seen in the carbonate example. So pH on the x-axis, and then on the y is the predominance of that species. You can see that at really, really low pHs, so in really acidic conditions, aluminum is fine being its own toxic metal ion on its own, floated off on its own, hydrated by water. But as we get more and more basic, these hydroxides are going to displace water and instead form these complexes. So how do we describe complex ions? Well, with another K. That's how we describe everything. And K sub F, or Kf, is the formation constant. And the higher a Kf you have, then the more stable that's an ion complex. And they're usually pretty big because the complexes are more stable than just an unreacted metal ion in solution, usually. So how do we calculate that? Well, we just do the same thing as everything else. So here's ALOH4 over our ALOH3 and then the base here. And so in this case, 1 times 10 to the 33rd power, it's a very large constant, and that is because in basic conditions, it's much more stable to have it as ALOH4 than ALOH3. All right, so the key concept here is that a complex ion is a metal ion with other molecules and ions surrounding it, and ions can form large complexes in solution, and these complexes have differing solubilities. All right, well, that brings us to the end of our solubility lecture. I will be back again to elaborate on this and talk about weathering. Thanks so much.